You guys missed it while you were gone. I turned the whole planet Earth into a black hole. And actually, we all fell into it, and we popped out into a different universe. Some theoretical physicists postulate that when a black hole gets created, that it is the Big Bang of a different universe. And I kind of think that idea might have some promise to it, actually. Yeah, I think that has some promising. It seems promising to me because it doesn't imply we have multiple universes. It just implies that all the universes are like nested Russian dolls, and that when our Big Bang occurred, that we're just part of a higher universe, and that there's black holes forming in our universe, and that's forming sub-universes. So that idea seems cool to me. But just because it seems cool does not mean it's true. Yeah, it makes sense, but it doesn't mean it's true. We have to go scientifically verify it. So it hasn't been scientifically verified. So at this point, it's just a guess. But that's how science and mathematics works. We make an educated guess, and we go see if it's true. Yeah, I like that idea, though. So actually, I was going to go over one more example, but I think we're beating the dead horse here. I think 4.1 is done and dusted. Let's start 3.2. Three 3.2 is about domain and range. Okay, so we already kind of talked about this stuff earlier. Okay. So set theoretically, remember, we define some set X, and we define some set Y. Remember, set is just a container of abstract objects. A set is itself an abstract concept containing other abstract concepts. Yeah, us math people are pretty abstract. So the X is the domain, the Y is the range, okay? So let's say, again, like last time, we put some elements in our set. Let's say this is A, this is B, this is C. Let's put some elements in this set. 1, 2, 3. Remember, a function is a map from one set to the other. Our function maybe can take A to 1, maybe it takes B to 3, and maybe it takes C to 2, you know. That's how I'm defining it. You could define it differently, okay? That's how I'm defining the function. So if you define the function this way, well, then you say, well, f of A is 1, f of B, then according to the function, it's 3, and f of C is the one that's remaining, 2. So the inputs, A, B, and C, are the domain. The outputs are 1, 2, and 3, okay? Another way we could have represented this information is using this set notation, where these squiggly lines are like the set. This is a set. Squiggly lines mean set. And we represent this map as a pair. The input comes in the first entry, the output comes in the second entry. So we list them. The input comes in the first entry, the output comes in the second entry. And the input comes in the first entry, the output comes into the second entry. Okay? So this is a set containing elements, and this is a set. Notice that all these are sets that we're talking about. There's one set, capital X, defined as the set of all A, B, C. Then there's another set, capital Y, defined as the set of all 1, 2, 3. So we've created a map between X and Y. And that map is this set. We call this set, which is a set of pairings, we call this a relation. We call this a relation. It's a bad A. Okay, and a relation becomes a function whenever you have a one-to-one correspondence. A relation turns into a function whenever you have a one-to-one correspondence, meaning for every input you have one output. Meaning that's secretly the vertical line test. The vertical line test is secretly for every input you get one output. So here's what I mean. Let's be given some function. All right. We know this is a function because if we test it utilizing the vertical line test, at any vertical line we draw, we realize it only touches the function once. As opposed to something like this, where the vertical line test touches the function twice. So let's see why this characterizes functions. Okay. Let's see why this implies for every input there's one output. It's best to show this set theoretically. Okay. Let's say I have 1, 2, 3, and let's say I map the image Y. 1, 2, 3. Okay. Now that our elements are numbers, we can plot them. Okay. Let me define a function from X to Y. Call it F. Let's map 1 to 1, 2 to 2, 3 to 3, and let's also mess around and map 1 to 3. Take a look at what happens when we mess around. We were good until we did that last step. We had a function until we did that last step. I'll show you what I mean. One, 2, 3, 1, 2, 3. Notice that 1 gets mapped to 1. I go to 1, I find 1, I put a dot. 2 gets mapped to 2, I go to 2, I put a 2, I put a dot. I go to 3, I find a 3, I put a dot. And what do? I connect the dots. Okay? So far, when I had not done this last map. So the maps we've done so far are this map. We've done this map, we've done this map, we've done this map. We've yet to do this last map. Notice what happens when I do that last map. Let's also send 1 to 3. I go to 1, I find a 3, I put a dot. And you know what we do when we put dots? We got to connect the dots. Uh-oh, SpaghettiOs. Because, take a look, the vertical line test, oh no. The vertical line test was working so far. Vertical line test was working, vertical line test was working. Oh my goodness, what's going on? You guys see what's going on? The vertical line the vertical line test failed whenever for every one input in the domain, we didn't have one output. For every one input, we needed to have one output. For one input, we now have two outputs. One gets sent to 1, but one also gets sent to 3. And because of that one very fact, it causes the vertical line test to fail. Yes. So that's why this ceases to be a function. So whenever I write out this in set theoretic terms with the squiggly brackets, notice that we get 1 goes to 1, we get 2 goes to 2, we get 3 goes to 3, and oh no, we get 1 goes to 3. So if you get presented such a situation where you get a bracket filled with entries, just see whether each input goes to one distinct output. Oh no, I notice 1 is getting sent to 3 and 1 is also getting sent to 1. So that cannot be a function. So if you have a graph, you can use the vertical line test. If you don't have a graph, you have to use this test. See whether the input maps to only one output. If you do that, you'll be able to determine whether something is a function or not. Also, you must realize that the first entries, they are the domain. And the second entries, they are the range. That's all you need to know to do the homework for those kinds of problems. So now that we have done so much abstract stuff, let's move to more concrete stuff. Let's deal with the functions we're used to with x's and whatnot. Find the domain of this function. What is the domain of f of x is equal to 1 over x? X is domain, y equals range. Yes, Cody. That's right. So the way we determine domain is the set of inputs that don't mess up the outputs, okay? So somebody could easily spot what input would mess this up. But to make it extremely, extremely explicit, I'll make an f of x table. Let's pick some symmetrical values about the origin. Okay. What is f of negative 2? F of negative 2 is equal to 1 over a negative 2, just a negative a half. That's okay, nothing wrong there. F of -1 is equal to 1 over -1. That's just a -1. Nothing wrong there. Everything's fine. You know, maybe everything works. Let's just keep going just to make sure. F of 0 is equal to 1 over 0, which is 0. 1 over 0, or you mean F of 0? F of 0 ends up becoming 1 divided by 0. Right? And what is 1 divided by 0? Undefined. That's right, Tyler. That is right. It's a black hole. So notice that this is undefined. So this input 0 cannot be in the domain. It cannot be in the domain. It cannot be in the domain. But notice if we keep going, F of 1, that's 1 over 1, which is 1. Hey, that works. And if we were to keep going even further, F of 2, well, that's just 1 over 2, which is just a half. So after that pesky F of 0, which messed up, everything else seems to work. So the domain, if it is the set of values that when you input into the function, it doesn't mess up. That means the domain D is equal to everything to the left of 0, jumping over 0, all the way to everything to the right of 0. This is how you write it in interval notation. This is how you write the equivalent thing in set builder notation. It's the set of all x such that x never equals 0. Or you can say, equivalently, you could say, x is greater than 0 and x is less than 0, meaning everything but 0. Oh my goodness, it's 8:24. Guys, why don't you tell me that class has been over for like 10 minutes? What do you guys enjoy, math or something? Did you ever think you'd be saying that? Be honest, did you ever think you'd be saying that about math? Never. No. That makes me really happy. All right. It's interesting to see how it works. Yes. Yes. That's the best part about math, is seeing how it works, why it works. When you don't understand that, math is no longer interesting. It just seems like a bunch of scribbles on a chalkboard that make no sense. Okay, so we got this far, all right? So I will push the homework back for 3.2 and 3.3. Okay, I'll push the homework back. So next week we'll have to cover those a little bit faster. No, but the black hole analogies have pulled me in. Pun intended. Yep, I have now pulled you into a different universe, an alternate reality in which you actually find mathematics enjoyable, correct? Because before you didn't, and nobody could blame you. I'm telling you, I didn't even like mathematics. I hated it. It was my least favorite subject. It was my worst performing subject as well. I did the worst on math, and I hated math the most. But theoretical physics put me on to math, and then I realized that even the theoretical physicists didn't know what they were talking about mathematically as much as the mathematicians did. So then I realized, okay, it's time to get serious and learn math. So not only is math cool on its own right, doing research in mathematics to create new mathematics for the sake of nothing. We create new mathematics just because it's fun. We don't create it for a purpose. The purpose is enjoyment. That's how pure mathematicians think. They're like, I'm creating this stuff. I don't care if it has real life applications. I'm just doing it because it's awesome. But theoretical physicists are more practically minded. They think, let's create some mathematics that correlates to physical reality, our universe, black holes, stars, space and time, electrons, stuff like that. So I like both. I like both equally. I'm very fond of pure math, and I'm very fond of theoretical physics. I like both. I aspire to do research in both. Okay, I'm gonna let you guys go. Feel free to leave reviews on ratemyprofessor.com. I'd greatly appreciate that. See you guys later. Let me know if you guys have any questions. No problem. See you later.